I've done it before. Hello everyone, it's October the 3rd. So we're gonna do jump game today, number 55. I've done it before, probably more than once. And surprisingly, it's a medium question today, Sunday. So we're gonna just do that one more time. Before doing it, let's see how many times I've solved this problem. I think it's gonna be Bob and Alice, if I remember correctly. Oh no, there's no name involved. All right, let's see how many times I've done it. I've done it once. May the 31st, 2 years ago, 2019. Wow. Oh, so this is I know what this is. This is during my internship. 2019, number 55. All right, let's take a look. Yeah, I definitely don't remember the solution at all. You're given an integer array. You are initially positioned at the array's first index, and each element in the array represents your maximum jump length at that position. Return true if you can reach the last index, or false. Now I remember the question. I don't remember how to solve it, but I remember the question. Oh my god. Ooh! Our cat just went crazy. Loco, muchacho loco. We got him a new toy, and then that probably stimulated him a little bit. Alright, so the first one we can jump 2 times. I think this is once, this is 2 time, and I'll jump once and jump once. That's why it's good, right? So jump 1, 2, 3. Oh, the maximum number of jumps. And then we can jump 3 directly to the last. Okay. So you always arrive at index 3, 0, 1, 2, 3, no matter what. Because that's jump 3, jump 2, jump 1, and then you cannot progress. Alright, so problem like this, 99 out of 100 times is going to be dynamic programming. So we just need to pick a good target for dynamic programming. So the question is whether we can jump right from the start. So we can say whether we can jump from here, right? Let's say if we can jump to the end from this position, and we're here, while we're here, so we look forward, like we have to jump this, we look at these 2 positions, and if any one of these positions can jump, then we're good, right? If none of these can jump, then we're bad. So, okay. So that is in position. So at this position, we can always jump because we're at the end. This position is true, right? In this position, we need to look 1 further. That's true. So this is true. In this position, we can go 3, right? So we just need to go 1. Whenever the first one we find that's true, and it's good. So this one is true, is good. And we're looking this is true, is good. So this and this one is false. We cannot go anywhere. So from here, I look 1 down, that's false. And from here, and look 2 down, right? And from here, I need to look 3 down. This will work, but it's going to be O(n) squared. And I'm pretty sure it's going to time out. Right, I'm pretty sure it's going to time out. Can we do it faster? Right, immediately. Can we know that immediately? Let's see. At any position, right, and we have the next group, right? And we just need to know if this group, this whole group thing, can be, a group, a range, right? So we're doing a range query. We're querying whether this range contains at least 1 true. Is that segment tree? A segment tree. I dread writing segment tree. Let me see. So this one is true. And this one is false. So this one's going to be true, right? And then for this, my target is this, right? So this is false, so this one's false. And when I know this one's false, so I need to update this range, right? So this range is going to be false, but this range is going to be true. So I query a range. Yeah, I think this is a segment tree. This is a segment tree. Can I use a BIT, binary index tree, to help with this? Oh my god, binary index tree. It's for querying, right? It's for querying. Let me see. I forgot how binary index tree work. Let me pull it up. So I think it's useful and binary index tree. Okay. Let's see. BIT. So and initialize the BIT, the size of the range, including min and max. So that's the entire range. So in this case, it's going to be the entire range, right? Entire range. And then update. Update the value at position by adding delta. By adding delta. So this is saying that at a position. So at a position, let's say at a certain position, I know it's going to be true or it's going to be false, right? So that's the delta. And then when I apply this delta to all the range, remember, each bit, each element represent a range. I forgot exactly how this range is represented, but each element represents a range. So we're going to say this range, right? So if this range is true, right, that means at least one of them is true. So if the range is true, then no matter what the current one is, the range is going to be true. But if the range is false, and I am false, and the range is still false, right? If the range is false, but I am true, well, basically, if I'm true, if the delta is true, then the whole range is going to be true. But if the delta is false and the range is false, a range is not true. If the delta is false, then we follow whatever the range is, because if the range is true and it's still true, and it's false and it's still false, okay, so we can update. Then query. What does the query do? The query returns the value from 0 to max R. So I think max R is max range, right? So max range. So we return this. So in order to find a range, we need to do this and this, right? So we're going to find the I see. Jimbo is scared. So we have the range here, and we have the total range. So if the total range is true, and this range is true, oh, we have no idea whether this range is true or false. That is not good. I need to know whether this range is true or false. Yeah, I won't be able to know, right? I won't be able to know. I feel like this should be segment tree, but how do I represent this? If the whole range is true, that means at least we have one true value in it. Then, let's say if this is true, and then any range will be true. If that's a problem, if this is true, any range will be true. I cannot identify. Can we represent it differently? I can't. How about we add value? If it's true, we add 1. If it's false, we add a 0. Okay? So then we have each range give us a value, right? if this range gives us a value, and say this range gives us a value, and then the difference, if this is true, then difference will be 1, right? And this gives us a value, and this gives us a value. So with this two value, if the two values are the same, then we know these two are false. That might work. That might work, actually. And we don't have to make too many changes to the BIT. Yeah, so what we do is we go from here, but we do it once, and every time we enter something, we query, right? We query, and after we query, we can determine what this is, and then we update. So every one, right, we query first, and then we update. We query and update, query and update. And then this, the last one, we query, and after query, we update this. Actually, we just need to query. After query, we can say if the query result is like it's 1 or 0, then we know if this is good or bad. Let's try this. Let's try BIT. Man, I'm trying to see how BIT look like. So we have this, and then because with +1, it was 1 based, right? So we're gonna do position +1, and then wow, this is smaller than every bit I, and what does this one do? This one is going down, right? Okay, I and minus I. Minus I, is that 2's complement? Let's do minus I. I forgot. Let me check. So let's say 2, right? 2. So let's say 2 and minus 2, right? 2 and minus 2 is 2. All right, 2 is probably not a good idea. Let's go 5. 5 and minus 5 is 1. I think it's finding the 5 is what? 5 is 1, 0, 1, right? That's 5. So minus 5, we do 2's complement, it's going to be this plus 1, right? So if we AND these two, it's going to give you 1. So I think it's I have to find the reverse everything plus 1. Find the rightmost, find the rightmost one bit, right? And then we find the rightmost 1 bit, and we can add to it, which is just OR it. Move that many space. It's we find that bit, and then we move. I just jump, right? I jump. So it's either going to be all power of 2, right? We plus power of 2, so some power of 2, some power of 2. Okay, so at each power of 2, we're going to do this. So at I position, and then I plus the power of 2 that I can get. At each power of 2, and I'll increment the same value. So that's the range, from the start to I, and then from the start to I plus the power of 2, and then plus the next power of 2, all the way to the end. Okay, so that's the range. All right, let's give it a shot. I still think I need to learn how to write segment tree, which I used to know, but segment tree always very elusive for me. Maybe we'll try, like, if this one works, we'll try segment tree too. All right, so first of all, we're gonna copy and paste the BIT code. Right? So we need a BIT. It's R, and the result just gonna add this, right? And then, oh, hold on, that's not, and we minus. So we're starting from this position, and then we go to the next one. I think unless you're power of 2, it's going to start from the start. If you're not power of 2, it's not starting from the start. It's just, yeah, we're adding this, and then we're adding this, right? And then we start from wherever I is, right? We have a bunch of 1s. So we're going to remove the rightmost 1, right? We remove the rightmost 1 because the bit I represents the range from this, I minus this, to I. So that is the range. Oh, okay. Okay. Maybe. Think again. I increment, right? And then we go for this, and then we increment. And then when I come to the reverse action, I'll check I first, right? We check whatever I first, and we get the value. So I say this value is going to be from this to this. How is it going to be from this to this? Because from here, I can grow, right? From this position, I grow. And then grow to whatever level. And then from that position, I can do reduce. Right? And every time I reduce, this, I'm going to add 1. And then when I add another one, and search for BIT, bit index tree. I've done this many times, but I still couldn't. Fenwick tree, yeah, I couldn't completely. No, consider the following problem. Specific array, sum of the elements. Just to create an extra array. Sum of the first I elements and ith index. Sum of a given range cannot be carried O1, but the update operation takes ON. Yeah. Very few number of update. Performs both. Less space and easier to implement. Each node, so the sum of some elements of the input array. The size of the tree is equal to the size of the input array. And the code below we use the size of n plus 1 for ease of implementation. All the values are 0, then we update for all the indices. Returns the sum of the subarray. This. I don't do that at all. Subarray using this, which is construct from initialize output sum of 0. The following while the current index is greater than 0. add bit index to sum to the parent of this. The parent can be obtained. The parent can be obtained by removing the last set bit from the current index. Index minus, this is the get, this is this one, the get. So get the current node, then we go to its parent, right? Its parent. The parent is removing, okay, while it's, so the parent is at a smaller value than the parent. I've seen this many times. Okay. Index of parent I can be obtained using the formula. Both formula removes the last set bit. Yes. Input array is this. BIT array. So So we're going to input 2 is here, right? And then we input 1. Now this is not helpful, man. Now, which one is which? 0, 1, 2. Okay, 0, 1, 2. 2 is the parent of 3 because two will have to add two is the parent of 3. Because 3 minus 1 is 2. Okay? So 4 is the parent of these. Just remove the 1s. Right? 7, remove 1 and be 6. 6, remove 1 become 4. Right? And 4, remove 1 be 0. Okay? So that means if we want to compute the sum, we go to the target is 7, right? And then 7 will store the values from 6 to 7. Right, from 6 to 7. That's where it's gonna store. Therefore, when you do 7, you obtain 6 to 7. And then at 6, you store from 4 to 6. So 0, 1, 2, 0. So 7, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 7 here. Alright? The sum is 16. 3, 4, 7, 9. Yeah, it's 16. That's true. Right? So which means if I am 7 coming in, I change myself. I change the 7, I change myself, and the 7 only records the difference. The sum between 110 and a 111, right? That's what 7 incorporates. But if you are 6, right? If you're 6, which is 110, 110. No, actually no. If you're 4, right? You're 4. If you're 4, that's 100. And then you need to add 1. Right? If it's 4, you add 1, it becomes 8. Yeah, 4 will become 8. and 4 will represent everything. 2 will represent also everything from 2 is here from start to 2. 5 is 101, which are representing everything from, because 5 is a parent, so we remove 1, so from 4 to 5. So 5 represents from 4 to 5. That's because when we have 5, we add it, and then we remove that, it's going to be this. Okay, so for each value, we add it, and then we increment. Now by incrementing, okay, what are we doing by incrementing? By incrementing, we plus 2, or increment to 4, increment to 8. Right? Basically, it's just, is that times 2? No, we're not times 2, just incrementing. Yeah, it's like we add this, we're incrementing, we add this, and incrementing, add this, and these are all in one line, right? They all follow, they all, when I increment, that become my children, right? That become my children if I increment, become my children. So I go the other way around. Now the children will contain, still no. So for each value, I contain from this to this. So from here, minus 1, and from this one, the plus and minus is different. If I'm 6, right? If I'm 6, that's going to be 110, and I'm going to add a 10, which is 2. This one will go to 8. And 6 will go to 8. So 2 is different. 6, I will go to 8. So in 8, I will include 6. Okay. Everybody will go to 8, right? 5 is 101. I'll add the 110, we'll add again from the 1000. So everybody will add towards this position. Yeah, that's true. Everybody will add towards that. So if it's 5, we add 1 and be 6. So 6 will contain 5. Yeah, 6 contain 5, but 6 is not, but 5 is not a parent of 6, because from 6, I need to move 2 to become 4. Hold on, I seem to gradually got it. I seem to gradually figure out the BIT. So for any position, right, I add the bit, and it's not my children. I just add this bit to say the next one, that thing, or including me. Right? The next thing, the one I add, will including me. For that thing I add, because I add the rightmost 1 bit, the next thing will have, so next thing will not be my children. It's not my children. That thing will incorporate a range different from me. It will incorporate a range including me, right? Because I add this, so it will trigger, right? Going to some level, and then that will include everything from its parent, right? From its parent to this, which include every single values in between. So I incorporate, the next one incorporate, everybody incorporates. Yeah, so when we build it up, right? When we build it up, and make sure the range for each I, the bit I represents the sum or sum operation from the current I and towards its parent. So in this range, it has the sum of this. That's why we will just add it up. Right in here, we add it up. Because this from I towards I and minus I. So this range, the sum is represented by biti. And then to create this biti, we are doing this. Right? But every time we plus delta, and every time we plus the I increment, that's not the parent. That's a different way. Like it's a different way. So every time I add and every time I minus, it's like two different operations. And it's still a little bit hard to wrap my head around. I add it, right? And we say in once I add it, then that one will include me, right? That the next thing will include me. The next thing will include me. So always add 2 to the certain power. And that means that one including me. Hold on. I'm almost there. So when I add, I'll reach certain value, and that value will include the value from that minus 2 to the power into this. So everybody will be included in this because I'm doing this operation. I'm adding, basically I'm finding the end point, right? The end range. And then each end range is represented by the ones contained in me, right? So we find the end range, we put myself in there. We find the end range, I'll put myself in there, right? And then when we going backwards from each end range will include everything until its parent, And if you are power of 2, right? Like this one, power of 2, then you're containing the entire thing from 0 all the way to you. Okay, so now I have a little bit better understanding of this. Update. All points can be represented as a sum of power of 2. Every node stores the sum of n elements, where n is a power of 2. That's correct. First diagram above, get sum. First 12 elements can be obtained by the sum of the last 4 elements. Because of 12, what is the binary representation of 12? So it's going to be 1 0 0 0, so that's 8, right? 8 plus 4, so 1 1 0 0 is 12. So it's going to be represented by 8 to 12. Well, I said 9 to 12, right? It's 9 to 12. Why is it 9 to 12? And a 1 to 8. Because 1 to 8 of a 12. 12 is because of plus 1. Don't forget. With plus 1. So we start actually, it's 13, right? And then minus 12 or minus 1. No, that's because it was 1 based, so that actually is 12. Right? And then 12 with a minus. Oh, we don't include. Oh, so that does not. It's 8 to 12, but did not include 8, so it's 9 to 12. And then 8 minus 8 is 0, so it's 1 to 8. I see. Yep. So that's also each position can be split, right, into different parts. And then we just go the sum of these parts. Okay, so I think I got a better understanding of BIT. I think it's the key is always with the query, so you know like what each bit I represent, right? Each bit I, if you can write I in a binary form, then bit I represents the range, the sum of the range from I downwards to I removing its rightmost one. So that's the range. And then to build up this range, we use this to build up this range. All right, it's good. Refresh on the BIT. I'm going to copy this one here because we're going to use it, but probably without all the, yeah, it's fine. Let's just keep it there. All right, so n equals len nums. Let's say BIT equals BIT. And we need to put n in it, BIT n. Okay. Now what? Now we are going to go from the last position, right? So go from the last position. Let's say for I in range, n minus 1, minus 1, minus 1, right? And then in the last position, what we're going to do, hope I can just get it smaller so I can see. Yeah, so in the last position, well, I mean, in the last position was always going to be 1. How do we do? The last position is going to be 1. So we can just say bit, right, dot update n minus 1, right, equals, the update position and delta. And position with delta are going to be 1. That's the last position. And then the last before, right? Then when the query, right, when you do bit.query, query what? Query the maximum R. So the maximum R is going to be represented by this and the maximum you can reach, right? So we're going to say the query result. So I'm going to say Q, right, equals bit.query. So query from the maximum range I can achieve. So what is the maximum range? Well, the maximum range is going to be nums I, right? It's going to be the current position plus nums I. That's the maximum I can achieve. And the minimum I can achieve. It depends. Like if I'm 0, yeah, I might just do this. Like if nums I is equal to 0, right? Then we can just immediately say bit to the update I. It's going to be a 0 because it's false, right? We cannot do. Else, when a query. So this is the maximum range I plus whatever I can do, but I have to have a min of this and n minus 1 because it cannot be larger than n minus 1. So let me query this, and then minus. Yeah, because I was looking from this one down. Should I build it from this one up? What am I querying? I'm querying from start to here, right? And then we'll query. Yeah, that's fine. So we're going to query this and minus bit.query, right? I'm going to query simply I plus 1. Right? There's a 2. One is the maximum I can reach and this. And I will get a query, which means how many, so within the range that I can reach, how many 1s there are. Now if Q, if this one is larger than, let's say just if this is larger than 0, right? Which means at least one of these as 1. That means I can say bit.update I 1. So I can update 1. Otherwise, if it's 0, then we have to update 0. Else, bit.update I 0, which means the only chance that we can do 1 is from here. So we can just copy this and do this, right? Because what if it's 0? Well, if min 0 plus, well, this is 0, so it's just going to be I. I'm querying myself. Well, myself has not been, well, it actually has. Querying myself minus querying something, querying myself and minus something querying down, right? And that is not going to work because querying down, this one shall always have a larger value. So it should be a smaller value. Which means it's this. Give it a shot. I think it should be fine. Oh shoot. Query. All right, I'm going to update 1. Otherwise, we'll update 0. Because I start from here, so I update this, and that's the solo one, right? There's no other things involved. And then I'm coming here, right? And I say I'm going to try the maximum. If this is 0, then we just stay where I am, right? And which means it's 0, because this one has not been populated yet. Because every time we populate, we go further down. Yeah, so this should be fine. So we do all that all the way towards this. And in here, we're going to say we're going to query. The last one, I'm going to query this position, right, all the way to what I can. And then tell me if it's larger than 0. If it is, and update this one to 1, right? Otherwise, I'll update this one to 0. So now, what do we do? How do I know? I can check this. And what I want to know is whether it's possible. I'd say I have an imaginary thing here, right? And what I want to know, I just go one step, right? So I just want to know this position. Is it possible to go from this position to the end? Which I need to do is query this position, which is query to this, right? So just query this. So we can just say when return bit.query 0. Right? We just query 0 by itself. And if it's larger than 0, then it's a true. Otherwise, it's going to be false. Okay? All right, let's give this a shot. So we have first 23114. This one's true. Next one is 32104. This one's going to be false. Nums can jump. Nums. Nope. Answer true, return false. Alright, we need to take a look at the BIT. So just print bit.bit. Comment out this. There's bit.bit, which should look different. So, okay, so bit.bit. That is not. Hold on. It should be I. Because I want, say, I'm here, right? I want to query these. So I query this minus, I cannot minus this. If I minus I plus 1, I'm only getting this. So I have minus this. So it should be minus I. All right, try this one. Now we pass. This one we pass. I mean, we can actually make it simpler by doing one less query, right? So what we can do is, instead of going to -1, we can go to 0, right? we go to 0, and at the end, we're just going to query when the return query. So we can save one query. So we return query. It should be 0. So it's going to be just nums 0, right? Nums 0 and n minus 1 minus 0, right? So to query, so it's just basically the largest we can go, and the minus query 0, so we have this. And if this is larger than 0, then I can go. If it's not, then we cannot go. So we can save one query. Right? Save one query. So, okay, now let's try. So we have to put the bit as well. Update this, then here I try it. Wrong answer. Oh, 0. Okay, that's the edge case. 0 shall be false, right? And the answer is true. Okay, it's okay. How does that happen? Because of this. Let's see, how do we remedy this? Well, the way we remedy it is, if I get our bit 1 bigger, right, and then from this position, if I can merge this into this logic, just from this, right, towards, let me see, so we query, so to know whether we can go from here, right, towards the end. So we have to, right, from this we have to go towards the end. So yeah, I think we can do, instead of doing this, we just go from here, right? And then this is the last one, and I'm gonna go n minus 1, right? So query n minus 1 and minus query, but that will always be, let me think. I plus, right? I plus nums, yeah. And then if the end, if we add one more element, we say we're gonna reach this element. So then we're gonna query this, right? And then we say this can always be reached. Yeah, we can do this. So instead of n, let's do n plus 1, right? And then I'll update n. Because this one will always be reached. And then we're going to go n minus 1 towards the end. And then this one will not pass, because this has to be n, not n minus 1. I have to go all the way to the end. And this one is the same. I have to go all the way to the end. Do we like this setup? Or, if we don't want to do this, we just reduce this. And then we're going to say, if, you know what, this is actually good. So we're extending, right? We're extending. So we are extending, we'd extend nums by one element, which represents the true end, right? Which represents the true end. This is used, right? This is used to also evaluate whether we can go. What if we end at 0? That's an interesting question. you can reach the last index. So we're saying if it's 0, it's a false. We cannot reach this position. So if we can reach here, but this one we cannot. It's easy. Let's test this. Let's test this. So let's try this. See what does it say? I forgot. It's a true. Right? This is a true. That's troublesome. If this is true, yeah, this will be false. So this is true, but if it's 0, and this will give us false. Oh, my output is false. Oh, it's different. My output is false. Oh, hold on. That is weird. That is weird. Hold on. -1, -2, and -1, and -1. This shall be true. Expected is true. Why? I already said bit. As 1, right? But of course it's 0. Which means that is not. So let's go all the way to -1, and we're just going to query one more time then. So we're going to query 0. There we go. That is the way to go. We'll query bit 0. We'll query the first bit. Okay. Run it. Now we're not extending anything. Nope, there's no extension. No extension. Same mode. Same mode. This is the last. Sorry, this is the last position. Always reachable from itself. Right. The last position is always reachable from itself. All right. Now I'm gonna try again. Judging. All right, we got it. Oh, you're very slow. 2000. Okay, so just give us 16%. It's pretty bad. So we use bit index tree. We need. I use. I'm going to say we need. I use a segment tree to check whether it is possible to go from any position to the end. For instance, right, given nums I equals 2, I check whether it is possible to go from I plus 1, from I plus 1, I plus 2, go 1, from I plus 1, or I plus 2, right? Or I plus 2 towards the end. If any of these two positions allow access to the end, it is possible to go from I to the end. Now this requires a query of a range I plus 1, I plus 2. More generically, for any I, we need to query I plus 1 all the way towards query I plus 1 towards I plus nums I, and then minimum value of this, and n minus 1. Right, so this is, we need to query this. A segment tree can perform such query and update, right? Update in log n time. I use the binary indexed tree implementation to simplify, for simplicity reason, The runtime will be on log n, right? Because we have on and each time is log n log n. So on log n time complexity, but we have a very bad runtime, 2072 milliseconds, 16% ranking. Let's take a look at the Java solution we have back then. 2 years and 4 months. What? That was very simple. Huh. Last equals, I equals last minus 1, If nums I is larger or equal to last minus I, nums I is the amount I can jump, is larger or equal to the last one minus I. Is if I can jump that much, then last equal I. So I go 1 by 1, right? I go 1 by 1, and then if at certain position nums I, and then it's larger or equal to, so last is here, I is here. So if I can jump from my position to this, my position becomes the last position, right? And I keep going backwards, right? And then if I can jump, then I just move, right? If I can jump, I move. If I cannot jump, just keep going until I find a position that I can jump. Then I move until I see if. Why don't you just return last equal to 0? This is greedy, right? The solution is greedy. So what we're saying is, if I can go this jump here, I immediately move, so I say I can jump to this position, right? I can jump to this position. And then I say this, I can jump to this position. And then I say, I can jump to this position. And then I can jump to this position. And then here, I cannot jump from this to, so I still remaining here. And in here, I cannot jump, so nobody can jump. Now, why does greedy work? So what does it mean? Like, if we have an end position, and then I have myself, right? And I say, I will be the one to make the jump. I will be the last one to jump, right? Like, it could be anybody before me can jump. Okay. If I can make the jump, right, then anybody before me, they can either jump directly to it or can they jump towards me to it, which means from my position, no matter what we do before me, from my position can always jump to the end. right? Because if somebody can jump beyond me, then they can jump to me to jump to the end. If somebody can jump directly to the end, which is jump beyond me, yeah, they can jump to me and jump to the end. So no matter what, right, no matter what we are finding, we're looking for right now is the latest point that we can jump towards the end. So as we go backwards, we're always trying to find the latest point that is available, which means the shortest distance that's needed to jump towards the end, right? The shortest distance jump towards the end, and then the shortest jump towards this point. And we don't care if you can jump beyond, because you can jump however much beyond you want. You can always jump through me to go to the end, because the question is not the shortest path, the shortest jump. The question is whether we can make this jump, right? So if we go backwards, right, we find the latest jump point, right? The latest jump point that can jump towards the end. So we set our target here, right? We set our target here, and we just gradually move our target forward until we're good. Let me read this one more time. Just make sure, because this is greedy, right? This is greedy. All right, so the goal is to see if we can reach the end. So the question becomes, if I can find the latest point, which is we cannot go even further, the closest point that we can achieve to get to the end, right? If we can find that, and that means if we have any point previously, it means if we can reach this point, then we're guaranteed we can go to the end. And there's no other point beyond me that is capable of going to the end. So I am the last chance, right? I am the last chance to go to the end. So I look for me. I'm the last chance to go to the end. So you cannot go anything beyond. I'm the last chance. So every time we try to find the last chance, right? The last chance along the way. If I can reach the last chance, then we're good, right? So for each position, when they go, they can either reach, like they can either not reach me, or they can reach me, or they can reach beyond me. If they can reach beyond me or reach me, then that's the same thing. They can reach the end. If they cannot reach me, then we just need to find the previous, right, the latest point ahead of me, or before me. So we just, every step, we look for the latest point needed, latest point, the final point that we need to reach in order to go to the end. And then as we go, we will get closer to the starting point. And we'll see if the latest point will become the starting point. Good solution. Very good solution. I used BIT to do this. So this can be solved without BIT. So yeah, I think this is greedy. Going backwards in nums, trying to find the latest, the last position. Last position that allows access to the end. The last position that allows us to go to the end. And we keep looking for this last position. Well, it's good, but there are many positions, right? But the last position, there can be many positions that allow access to the end. But if we identify the last position, then we automatically include all the other positions, because if any position before the last position can reach the end, then those positions must be able to reach the last position. Let's just label the last position, let's say I, such that access to the end is possible. Right? There can be many positions that allow access to the end, but if we identify I, right, then we automatically include all the other positions, because if any position before I can reach the end, then those positions must also reach I, right? Must also can also reach the end through I, right? And that's the key. We can reach the end through I. So if we find I, we're including all possible ways to go to the end. So we keep finding the last position until we reach the beginning. Right? If the first element is also the last position to reach the end, we say the jump game is possible. Right. I got this solution from my previous attempt in May 2019. I must have read the solution. But anyway, so what is it saying? Let's say last equals to n equals line nums, right? Last n minus 1 for I in range n minus 2 to the start. So if nums I, right, if I plus nums I is larger or equal to last position, right? If I can reach, then last position equals I. So that's the latest we can reach the end. And I keep going, and then we return last equals 0. Yep. No need for binary index tree. Yeah, much faster. So this one's ON with 464, 90%. Two lines greedy. DP with complexity ON squared. Well, yes, I know what they're talking about. DPI is the minimum number of steps to reach position. On each step, we need to check potential n jumps. That's ON squared. But complexity using greedy. Okay, running maximum of these values. Check if for some element I, we're stuck and we cannot reach the last cell. If not, we can reach. Biggest index we can reach after say I jumps. Yeah, I'm pretty sure you have a number of jumps too. Okay, one jump can reach index 2, and after, okay, what is the idea? What is the biggest index we can reach after say I jumps? Then if we have new index to traverse, to update our range. For example, for nums of t? What is t? The biggest I can reach. Biggest I can reach. After one jump, we can reach index 2. And after each new index process, we expand our window, bigger value than the end of window, and increase the total number of steps. Do not do anything. So we accumulate this and max I plus num. So I is 0 plus num. And what is t? I plus value. What is this? This is the maximum position we can reach, right? And in this position, the maximum I can reach is 2. In this position, maximum reaches 4. How is in this position? Now we use accumulate, which one use max. But this one will be 0, right? And now we just accumulate. What is max does? Are you just accumulating it? 2, right? 4. That's 0, 1, 2. Accumulate. Put up, say there's 2, right? That means 4. Maybe 2. 3 will be 4. 4. 4 will be 8. And then we accumulate it, right? Accumulate will be the maximum value so far. Oh, so it's going to 2. Max is 4. Max is 4. 4, 8. Right? So at each position, the maximum I can reach. So for 2, the maximum I reach is 2. For this one, for 3, the maximum I can reach is 4. And for this position, we just say like overall, like to here, what is the maximum I can reach if I go through the previous? For some element, 2, 3, 4, I is equal to this, which means from start to I, the maximum I can reach is I itself. If stuck, we can now reach more. If not, we can reach. So we do this, and now we check all of them is not equal to. The maximum steps we can reach. That's a good one. That's a good way to think. The maximum. So basically, right, what we're saying is, given these steps, what is the maximum I can reach? So like given the first step, what is the maximum I can reach? Given 2 steps, what is the maximum I can reach? Well, given 2 steps, the maximum I can reach will be the maximum I can reach in the first one, and the maximum I reach in the second one, right? And then the maximum I can reach after the first three. What will be the maximum I can reach? The maximum I can reach here is going to be smaller, but the maximum I can reach this. So we need to take the maximum value among these, right? Maximum value among these. Well, would it be possible? What if I have, say, like 2, 0, no, 1, say 1, 0, 10, right? The maximum I can reach in the first one will be 1. Maximum I can reach in the second one, this one will just be 1 by itself. The maximum I can reach this, 2, will be 12, right? And now we run position. We can just say the maximum value. The first one, the maximum value is 1. Second one, the maximum value, and the previous one. Yeah, if I can reach, then we use this maximum. If I cannot reach, what if I just keep going? Oh, it's fine. Like it's fine. The maximum I can reach, if I can reach this position, right? The maximum I can reach if I hit. If I'm at this position, what is the maximum I can reach? And then that will be the maximum I can reach overall, right? Overall. But that doesn't mean that we can actually reach this position. So we go through again and check if at any position, if the maximum I can reach is equal to my current position. That means I cannot reach any further. So that's, good solution. I think it's the same as this, but actually I like this explanation better. The maximum you can reach at any position is the maximum you can reach overall from the start to you, right? Potentially, the potential max you can reach. And then we just run through this again, right? If at a certain position you just like you cannot reach further, right? If you cannot reach further at a certain position, and that simply means anyone previous to you, the maximum they can reach is you, right? If you cannot reach further, they can reach is you. Yeah. And then from you, if you can reach further, you will be bigger than yourself. Nice. This is actually good. Very good. Very good. Yeah, no reason to comment. We know this is a good solution. Don't make questions difficult. Reach is this, if this, if it's reach large event is nice. Yeah, just at each position. At each position we check what's the largest we can go. Right? If at each position, and we also have the previous largest reach, right? And my position, I have the previous largest reach. So the largest reach I can get from my position will be the maximum value of the previous largest reach and my largest reach. And if is it possible that previous largest reach doesn't reach me? Well, if the previous largest reach doesn't reach me, then it will reach something previous. And then that position, that previous largest reach will reach that one, and then that one will determine. So it's all fine. So the previous largest reach and my current largest reach, and it's going to be the maximal difference between these two, which is exactly this. And if these equals, yeah, this is a good too. Good. So I think I'm gonna post just for fun. Like let's do this. Binary index tree. DP-ish idea using binary index tree. This is not the fastest solution. Fastest solution is greedy. But this is an extension, right? Not extension, an improvement from a naive DP solution. In the naive DP solution, at each position, right, we will check all the next position, next reachable position. We check each of the next reachable positions and determine and see whether any one of them can lead to the end. This apparently causes the O(n) squared, right, runtime. To speed it up, we can use a segment tree. Right? We use a segment tree to perform range query. To simplify the implementation, we can rely on the binary index tree. So this, and this. See how it looks like. Yep, fine. Let's move this one, and let's post. All right, I think we're done today. Good. I mean, we figured out the DP-ish solution using BIT, but I didn't realize that it can be solved with greedy. And honestly, actually, I like the other greedy idea. You know what? I wanna write the other greedy idea. So this will be a greedy idea, a better implementation of the greedy idea, and I actually like this person's solution. This one's, I like it better. Reference. Right, so the idea is, find out the maximum position reachable from the current position. Now, as we traverse through nums, the maximum position reachable directly from I is I plus nums I. But it is also possible that the positions prior to I can have a longer reach. Thus, the max reach at I is the maximum of previous reach, right, and I plus nums I. Now, it is possible that the previous reach cannot reach I. In this case, we should have encountered this situation when such previous reach is encountered. Right. Say pre-reach is I minus 1, right? And then which doesn't reach I. Then we should have handled this situation at position I minus 1. Now, if I minus 1 plus nums I minus 1 is larger than I minus 1, that is, nums I minus 1 is not equal to 0, then our previous reach would have increased, right? Would have increased to beyond I minus 1. Now, the only reason that it does not increase is that we are stuck at I plus 1. Now we can check it. We can check it by examining whether the max reach at I minus 1 is equal to I minus 1. Alright, so now we're going to say pre-reach, right? I'll just call reach equals 0. And for I num, in enumerate nums, right? I'm going to say reach is going to be max reach and I plus n. Right, so if reach is equal to I, return false. Otherwise, return true. Ooh, that is not correct. Let's see what happened. I plus n. N is 0, I'm stuck at I, right? And if each equals I, and I is not equal to, okay, we have to say each n equals line nums, right? And we can call this just num. I not equal to num, and not num, and minus 1. If I is equal to n minus 1, then we just let it go. All right, try this one. This is a much better, I think. Yep, it's good. All right, that shall be it. I will see you guys tomorrow. Adios.